So here we're going to go over the history of kind of how we got to the here and now today on Earth. So we're going to go back into deep time. So if we look at Earth's evolution, we're going to have to go back to the beginning. And the beginning means we start off with the 13.7 billion year ago event that's called the Big Bang Theory. And this is just saying that there was this point of singularity where the entire universe was completely condensed into one infinitely dense, infinitely hot point. And all the matter and energy that were located in one particular location, something occurred and everything moved out from that one point. Now, some have referred to it as an explosion. You know, the bang implies something combustion, but it couldn't have been that because we didn't have the ingredients for combustion. So, but something happened, and it's referred to as the Big Bang, but definitely something happened. So this tremendous amount of energy expanded, and the universe had become born. And this essentially, in the earliest parts of the universe, it was dark. No nuclear reactions within the core of stars had begun yet. It was even too hot for low-mass hydrogen to exist. So for the first couple 100,000, even into a couple million years, it was so hot, elements couldn't even form. So everything was just like this soup, this ionized soup that wasn't even cool enough to begin for elements to, even the simplest elements of hydrogen. So if we fast forward 10 billion years, right? So we've already gone through, after 10 billion years of the universe having existed, our solar system has the right ingredients. And we're going to call this the nebular hypothesis. It has this dust and gas and ice and rock and metals and all these different materials that we can kind of, we can't see them, but they're located in this debris here, this debris field. And so what we do is we use this nebular hypothesis. It's the working concept as to how solar systems form and evolve throughout the cosmos, not just locally, not just our neighborhood, not just our explanation as to how and why. So other solar systems are forming this way right now, and we can observe them directly, right? Instruments allow us to do that. Remote sensing technologies. We have all kinds of different satellites that are pointed in different directions that are observing solar systems forming. Now, a solar system, make sure that you recognize that a solar system is simply a gravitationally bound series of planets with a star at the gravitational center of where these planets are orbiting around. So, and those planets, based on different locations, will have different characteristics. So we've discovered several hundred planets orbiting other stars, and this is continuing to increase as technology increases. So we're going to start looking into nebular hypothesis, and we have to realize that there's a heck of a lot of stuff out there. So a large class, which we can call a nebula, begins to condense. Most of the mass is in the center. There's turbulence in the outer parts. These turbulent eddies collect matter, measuring meters across. When it says collecting, really we're talking gravitationally kind of binding and bound to one another. And as they collide, they're growing. They're growing in the material that they have. And this is the accretion part of an evolving solar system. So the nebular hypothesis, again, these are just Hubble telescopes showing stars being born, right? Before we have a solar system, we typically start off with the focal point or the fixed point that gets most of the mass, and that would be the star that's located at the center. So here we have just different pictures here. Gravitational attraction causes the mass of the gas and dust to slowly contract, and it begins to rotate. Now, we can look at this in terms of the laws of physics that are identifying the conservation of angular momentum. And as a result of this contraction and rotation, a flat, rapidly rotating disk forms with the matter concentrated at the center, and that becomes the first sun, or the proto-sun. It's kind of this primitive, it's kind of not completely taking part in nuclear reactions, but it's begun. So it begins to light up, but it hasn't completely evolved into its defined spherical shape, but it's beginning to, and this is what we call a proto-sun. In this case, here's a false color image of a protostar in space somewhere, and I don't actually know where this is located. I didn't research that. But the multicolored area shows a dust disk surrounding a newborn star. So the cooler temperatures at a distance, and when this is a relative statement, they are less cool, but still would be extremely hot to our standards today. And then the center part where the nuclear furnace is burning is going to be the location where we find this red coloration. It's just a false color image here. And this is where this is where our sun, or any star. And after sufficient mass and density was achieved in our sun, so let's go back to our solar system here, the temperature rose to about 1,000,000 degrees Celsius, resulting in thermonuclear fusion, where at the core of this we have these hydrogen that are literally being compressed and squished under heat and pressure, and we're forming helium and energy. And this energy that's being released is the form of sunlight. It's really the direct conversion of matter into energy. And we can kind of quantify this, or even we can quantify it, we can use terms, explanations of this, by looking at Einstein's E equals mc squared, where energy equals mass times the speed of light, c squared. Matter is converted into pure energy and light. I take these 4 hydrogen, in the end, my outcome would be 1 helium plus energy. So the light is really the result of the conversion of pure mass or pure matter into pure energy. And those are the photons. Those are the lights that we see on a daily basis. Those are the photons that drive life on Earth. So the birth of a solar system here. So here we're looking at these certain regions. So we've got this protostar beginning to evolve and organize itself, assemble. And in these regions of space outside of the star, you have different compositions. You have different materials that are going to then build these different planetismals, or the planets that are in their accretionary phase. They're building. So the enveloping disk of gas and dust forms grains that collide and clump together into small chunks of planetismals. And this is what's happening in all of these locations. If you have a lot of rock and metals, they're going to accumulate in that location. If you have a lot of gases and dust and ice, they're going to form further out. So really, if we look closer to this location, closer to the protostar, it's going to be hotter. And if we get further, it's going to be colder. So when we talk about protoplanets, it's simply from this nebula, it begins to condense this protostar in the surrounding regions of space. They're going to then accumulate or accrete, gravitationally pull this material together, and then evolve into the planets as we know it. So it's the gravitational forces that are allowing the inner planets to accrue and compact the solid matter. And the further we get out, these are the planets that are collecting and condensing into gas giants in our particular location. And then the leftover debris are the comets and asteroids. They're still moving around in space. So our solar system is really the result of this nebular region and gravity kind of acting together. Gravity is going to organize. It's going to allow for planets and stars to pull matter into themselves, creating this growing effect. So the evolution of a planet or a solar system is really just how gravity is going to have particles accumulate the surrounding material. And here's just a picture of the planets where we have Mercury, Venus, Earth, Mars. We have our asteroid belt. We have Jupiter, Saturn, Uranus, Neptune, and now Pluto is considered a dwarf planet. Here we're just looking at these maps here, color-coded to display different elevations. So they have different topographies. Obviously, the different building materials, they've evolved a little differently. So here when we look at the age of the Earth, we actually don't study the Earth. We don't measure items on the Earth necessarily per se to get the Earth's age. Instead, we study objects that are in space, that evolved at the same time as the nebular hypothesis leads us to believe that everything formed at the same time. So meteorites, we date these using radioactive isotopes and their decay products. We get these ratios just like we've done in class. So when we look at the evolution of the planet, here we have just a sequence of what led to life on Earth and then how life has evolved through here. And you can take a look at this. You can pause and snoop through here. Today's not the scope and scale of what I want to get into. But the earliest parts of the Earth, for about 500 million years roughly, right here, 500 million years, was called the Hadean period. That these collisions, these mega scale collisions, just from debris that was in space moving around, these collisions were very normal, very common. And we got the moon out of it. It's called the giant impact hypothesis, that around 50 million years after the initial creation of the Earth, that a Mars-sized planet collided with it. And so if I look at this from a detailed standpoint, we get this oblique angle. We get this impact, a glancing collision, if you will. And then the debris that was thrown out into surrounding space then accreted into its own, let's just say, gravitationally pulled together the surrounding material, and that formed our moon. And then the moon has been gravitationally stable ever since. So we've got this collision that took place during the Hadean, during this heavy bombardment period, And when we look at what took place here, part of the material from the collision remained in orbit around the Earth. And this is just the debris field is kind of an artist's depiction of it. So before we move into the next part, make sure you understand how the moon formed, because this is all consistent with the timeline of what we know about the Earth itself. So the early Earth is really hot. We've got these collisions, we've got compression of the Earth itself, and we have radioactive decay of different elements within the Earth itself. So you've got these three features that are heating up the internal Earth. And this led to differentiation, that the internal Earth has this high concentration of iron in this liquid primitive Earth that's sinking into the core. As we know, the interior core is primarily iron. And this is called differentiation, that the different layers are the result of the different chemical compositions and densities. Denser material is going to sink, lighter material is going to go to the surface. And the Earth's crust is actually the lightest frothy material. The continental crust is the lightest, the least dense rock on the planet. So we've got this chemical differentiation, and these are based on what minerals are composing the Earth itself. And here we can look at the whole Earth has this composition, but the Earth's crust has a slightly different composition. So when I look at the composition of the Earth's crust, it's highly silicon and oxygen. But when I look at the Earth as a whole, it's got a heck of a lot more iron. It's just not represented in the Earth's crust itself. And that led to these layers: the lithosphere, the upper mantle and crust, which is both continental and oceanic. And then beneath that, we have the asthenosphere. We have the mantle itself, which is the largest chunk of the Earth itself. We have the outer core, liquid outer core, and where we have convection currents driving the magnetosphere, right? Charged particles moving around a solid iron core. And then we have the solid iron core. And as we kind of begin to finish this up, we start building continents. When the oceans, so volcanism is building continents. When oceanic crust is taking place, oceanic crust is being driven by these upper mantle currents that are creating oceanic crust. So we know what the Earth's interior looks like today by studying seismic waves. It's like an ultrasound, where we can actually see what is taking place within the Earth in areas where we cannot see, view, or observe directly.